Well, this time we're going to talk about more kinetic energy. Ball A has half the mass, but 8 times the kinetic energy of ball B. What is the speed ratio of A speed to B's speed? Well, if A and B had the same speed, then A would have 1/2 the kinetic energy of B. Because remember that the kinetic energy is 1/2 mv squared. So if the speeds were the same and we halved m, we would have k. But that's not what happens. We actually have 8 times as much, which means that we must have something which is, if this is 1/2, then we have to ask here, this has to be something which is 16 times as much. The v squared part has to be 16 times as much. But for v squared to go up by 16 means that v had to go up by 4. Because then when we squared the 4, we get that 16 factor. So we have that that A has to be 4 times as great as in speed as B is. If you didn't like that semi-mathematical reasoning, a straightforward way to do it, although a little complicated, is actually just take the ratio. Since everything's in terms of B, we can say, well, the ratio of A's kinetic energy to B's kinetic energy, which we know will be 8:1, and then we just set up what they're equal to. Ka is equal to this, Kb is equal to this, and we can say, well, if we have that, we can say, well, we have this half cancels with that half. Down here, I guess you can say. And of course, the MBs cancel out and the KBs cancel out. And that's how you get the thing over here. 8 is 1/2 of VA squared over VB squared. We group the squares and we bring the 2 over and we end up in the same place. The VA over VB is 4. All right, this is something called an energy bar chart, which will be relatively straightforward. We represent the energy as bars on this chart. We're not that creative when we come up with names in physics. So the velocity of a tugboat increases from 2 meters per second to 4 meters per second in the same direction that the force is applied for 20 seconds. Fill in the missing bars for the work and kinetic energy bar chart in this process. Well, in doubling, right, we have the kinetic energy is 1/2 mv squared. If we double V, the new kinetic energy is 1/2 the same mass times quantity 2v squared, or 1/2 mass times 4v squared. Oops, sorry. Or 4 times the quantity 1/2 mv squared, which is 4 times the initial kinetic energy. So if our initial kinetic energy was represented by 2 blocks, then our new kinetic energy has to be represented by 8 blocks. 2, 4, 6, 8. And since the work is the change in kinetic energy, it must be 8 minus 2, or 6 blocks. Oops. Better if I could count. 2, 4, 6 blocks. So that's our work done. Notice that the 20 seconds played no role whatsoever. It was just a distractor. All right. The tugboat over velocity changes from 2 meters to 4 meters per 2 meters per second to 4 meters per second in the other direction as a force is applied to the tugboat for 20 seconds. Fill in the missing bar charts. Well, the key thing here is to say if the initial kinetic energy was 1/2 mv squared, then the final kinetic energy is 1/2 m, and we have 2v squared because we have twice the velocity. And hey, that's the same. So we know without thinking, 2, 4, 6, 8. 2, 4, 6, 8. We get this. Which implies that we have 2, 4, 6. This many units of kinetic energy. The key thing here is to notice that it didn't matter which way the tugboat's going at the end, only that it's going at 4. Energy is not directed. A 3 kilogram block slides along a frictionless surface at 6 meters per second. It then enters a region which is 1.5 meters wide and where mu equals 0.3. What is its kinetic energy before it enters the frictional region? Let's draw a little picture. So here's our thing, and we're saying that it's mostly frictionless, but over here we have stuff, and that's 1.5 meters, where mu equals 0.3. And our block, oops, it's a pretty bad block, has some initial velocity, which is 6, and we want to know right before it reaches here, what is the kinetic energy? But that's okay. We'll call that our initial kinetic energy. That's easy. It's 1/2 the mass times the velocity squared. So 1/2 times 3 kilograms times 6 meters per second quantity squared. So we have something like 1/2 of 36, which is 54 joules. Same setup, and we now want to say, what is the change in kinetic energy between when it enters the region and when it exits the region? All right, well, the change in kinetic energy is the work done, but the work done is going to be the work done by friction, because it's the only force that is not perpendicular to the direction we're talking about. The work done by friction is going to be the force of friction times the distance times the cosine of the angle between them. And we can see here that the displacement points this way, but friction points that way. That angle is 180 degrees, whose cosine is minus. The force of friction is going to be mu times the normal force times d. And the normal force is going to be the weight. So the change in kinetic energy is going to be minus mu mgd, or negative 0.3 times 3 kilograms times 9.8 meters per second square times 1.5 meters, which turns out to be negative 13.23 joules. Same setup again. What is the final velocity of the block after it exits the friction region? Well, delta K by definition is Kf minus K initial. So K final is K initial plus delta K, or 54 joules plus minus 13.323 joules, which turns out to be 40.77 joules. But also, K final is 1/2 mVf squared. So Vf is twice the kinetic energy over the mass square rooted, or square root of 2 times 40.77 joules over 3 kilograms, which is 5.21 meters per second.